Welcome to all in this lecture. In this lecture, we are going to discuss a complex examples on beam. So let's start. This is our example. Determine the reactions developed. Okay. From this point to this point, the beam is there. At point A, there is a fixed support. From point B to C, the span is of 3 meter and a uniformly distributed load of 2 kN per meter is acting on this 3 meter area. From C to D, there is a uniformly varying load. Okay. And at point C, the force is 2 kN per meter, and at point D, the force is 1 kN per meter. Okay. And from C to D, the length is 2 meter. Okay. From point D, at a 1 meter distance, a 4 kN force is acting, and at a 1 meter distance from this 4 kilonewton force, okay, from this 4 kilonewton at a 1 meter distance, a clockwise moment of 3 kilonewton meter is acting, okay, at the end of the beam. So first of all, to solve this problem, we need to do something about this force, this load, okay, about this load. So first of all, we need to divide that load. Okay, see here, I am dividing this load in this compartment. I am making 3 compartment of this load. Okay, this total part is of uniformly distributed load of 2 kN per meter. We can easily solve conditions for this area. Okay, now consider this part. Okay, at point D we have drawn a perpendicular. Okay, so it will be a uniformly distributed load. And at point D the force was 1 kN per meter. So in this area, this green area, there will be a uniformly distributed load of 1 kN per meter. Okay, we got that. And now lastly we have this area. Which area? This area remaining. Okay, and this area is a uniformly varying load. Okay, at point the force was 2 kN per meter, and at point D the force is 1 kN per meter. So 2 minus 1 will give 1 only, will give 1. Therefore it is a 1 kN per meter force which is uniformly varying load. So let's see first about this part. Which part? This part. Okay, this is uniformly distributed load. See here, this first part is a uniformly distributed load of 2 kN per meter. This second part is a uniformly distributed load of 1 kN per meter, and this third part is a uniformly varying load of 1 kN per meter. Okay, now solving this, first of all we will find a point load for the uniformly distributed load of part 1. So the point load will be 2, that is the total load, into this 3 meter span, that is 6 kilonewton. Okay, and it will act at point L by 2, that is 1.5 meter. Okay, see here, for part 1 there is a uniformly distributed load of 2 kN per meter, and the distance from point A is 3 by 2, that is 1.2 meter, and the magnitude of the point load is 2 into 3, that is 6 kilonewton. Okay, we got this. Now consider the part 2, which is a uniformly distributed load of 1 kilonewton per meter. The distance from point E. Let's see what is the point E. See here. Okay, this is the point E, and from point F, the distance from point E and point F will be same. Okay, that is the distance from point E and point F equal to 2 by 2. Why 2 by 2? The length is 2 and that is the span is 2, and we have to divide it by 2 for finding the midpoint. Okay, so we get 1 meter, that is from point E and from point F at a distance of 1 meter in middle of them the force will be acting, and the magnitude of the point force or the point load we say is 1, that is the at point D. See, at this point D, the force acting is 1 kilonewton per meter. So 1 into the span, that is 2, that is the point load for this part 2 will be 2 kilonewton, that is 2 kilonewton. Okay, we get here 2 kilonewton. Now the last part is the third part. Okay, so the diagram for third part will be some like this. At point E and F, we know that there was a uniformly distributed load below it. We cancel the load and we are seeing only about this load. We can see that it is acting on the beam. We can consider it like that. And here at this point there was a 2 kilonewton per meter load, and at this point there was 1 kilonewton per meter load. So we did 2 minus 1 equal to 2. So 2 minus 1 equal to 1. Sorry, 1. So there is a 1 kilonewton per meter load of uniformly varying load is acting over this point. Okay, so for part 3, see here 1 kilonewton per meter load is acting. Distance from E is 2/3. Why 2/3? See here. Okay, at this point the force will be maximum near F, and the distance from F will be 1/3 into the length of span, and the distance from E will be greater, so it will be 2/3 into L. Okay, the point force will be acting near to F and will be 1/3 into the length of the span. Okay, so moving forward, see here from point E it is 2/3 into 2 equal to 4/3 meter equal to 1.33 meter, and from F it will be 1/3 into 2, that is 2/3 meter equal to 0.66 meter we get. Now the magnitude will be the area of the triangle, will be the area of triangle. So how we will find it? First we will take half into what? Into what? See here, we will see the first slide. See here, basically here the length was 2 meter, this is 2 meter. Okay, and it is 1 kilonewton per meter, 1 kilonewton per meter. So we get half into 2 into 1, that is 1 kilonewton load. The magnitude of the point force will be 1 kilonewton load. So we will summarize all of this and we will draw a total diagram for it. Okay, first of all, at this point A there was a fixed load. So a horizontal force RH is acting on point A in a horizontal direction towards the positive x-axis. A vertical reaction RV is acting on point A in a vertically upward direction, that is y plus axis. Okay, and anti-clockwise movement is acting on the point A. Okay, summarizing this 2 kilonewton per meter load, that is a uniformly distributed load at a distance of 1.5 meter, this 2 into 3, that is a 6 kilonewton load is acting at a 1.5 meter distance from point A. Okay, now see here at this point. Okay, this area, which area? This area. Okay, this was a uniformly varying load. It is acting at a 3.66 meter. How 3.66 meter? From this point it is 0.66 meter, 0.66 meter. Okay, and this 3 meter, so 3.66 meter. A force is acting of 1 kilonewton. Okay, And now this 2 kilonewton force. This 2 kilonewton force comes from the uniformly distributed load of this part. Okay. And it is acting at a 1 meter distance. At a 1 meter distance from this point. So 1 plus 3, that is a 4 meter distance from point A for this 2 kilonewton load. Okay. And from this point at a 1 meter distance a 4 kilonewton force was acting. So this 1 meter, this 2 meter and this 3 meter. So at a total of 6 meter distance from point A, a 4 kilonewton force is acting. And at last a 1 meter distance from this 4 kilonewton, a 3 kilonewton meter moment is acting in a clockwise direction, that is a positive. So now first we will find the summation of moment at point A and it is equal to 0. Okay, equilibrium condition. So first we will find the moments, all the moments acting at point A. So first moment is itself at point A in a anti-clockwise direction, that is minus ma, minus m at the rate of A. Okay. And now see here, a 6 kilonewton force in downward direction. So it will move in a clockwise manner. So plus of 6 into distance, that is 1.5 we will take. Okay. Now this 1 kilonewton of force, and in this way it is a clockwise manner. So 1 into 3.66, what it is? It is positive. Now 2, in the same way positive of 2 into distance is 4, and in the same way 4 Newton. So positive of 4 into 6. Okay, 6 meter is the distance. And at last this 3 kilonewton meter is a clockwise, so it will be positive, so plus 3. So summarizing all of this, we get the equation in this manner, this much big equation, and solving that we get the moment at the point A is equal to 47.66 kilonewton meter. Okay, now moving forward, see here. Okay, here at x-axis only RH force is acting, there is no other force. So we get that summation of Fx equal to 0, therefore RH equal to 0. That was a simple thing. Okay, now moving forward, the last example about the last thing is that we will take the summation of Fy equal to 0. Summation of Fy equal to 0. Okay, now we will take this RV positive, that is in upward direction. It will be minus 6 kilonewton because in downward direction. This is also minus 1 kilonewton, minus 2 kilonewton and minus 4 kilonewton. So summarizing all of it, we get RV equal to 13 kilonewton. So that's how a complex example on beams is solved. In the next video, we are going to take one more example about the beams and then we will end this series of beams. Thank you for watching the video. Thank you.